is absolutely amazing.
Yeah, so like 13 months ago, Israel exhibited the world's largest ballistic missile attack in the history.
Yeah.
Imagine that.
Wow.
300 of such ballistic missile with nearly 1 ton of explosive in each missile
Wow.
were fired to our cities, our houses, our kindergartens, our hospitals, our families. This is what happened. And the outcome, imagine what's happened if the US was exhibiting but such an attack from, I know, adversary at scale. It was, and it was all over the news. And there was nothing that any normal human being could do about it.
Right.
Nothing. Because these missiles are so strong, so explosive, that if it hits a house, it smashes the entire house and kills all of the people. No house, no people.
Mm.
So statistically, now you're in a casino, gambling on the lives of either your family, your friends, your beloved ones. I don't want to talk about, about properties, like houses and vehicles. And this is exactly what happened 13 months ago in Israel.
Wow.
And we saw the launches in our news, and we knew that these missiles are coming at us.
Wow.
The results, 0 casualties at our side.
That's crazy.
0 casualties at our side. Minor damage to some properties because of some residuals, right?
Right.
0 casualties. You know what I did in that night? I took my family to the living room, made popcorn, and watched the interception live.
Wow.
No shelter, nothing. I told my wife and kids, we're going to intercept all. You're safe. Let's have some fun. And we had fun. And we had fun. And I knew that we are going to intercept this attack and subsequent attacks because I saw the Israeli array of air defense solutions, the multi-layer air defense, from the moment they were an idea and a set of equations and spreadsheets.
Wow.
Till the deployment and consistent operational proofs in protecting our lives.
Wow.
So although the attack was new, this is intercontinental, it's a ballistic missile with much larger warheads. I knew that we will be protected by the Israeli air defense array.
That's
Okay?
amazing.
And you can say you gambled the life of your family, but it wasn't a gamble. I knew the percentage, I knew how the system works, I knew we will be protected, and that's exactly what happened.
Wow.
To complete the details, 6 months afterward, Iran launched similar attack with improved missiles, and again, it was completely intercepted, no casualties.
Wow. That's amazing.
Yeah,
I mean,
it's amazing.
Ballistic missiles and the number of missiles, that's the thing, right? Because this system has to be able to identify every incoming piece of ordnance and then separately launch and track for each and every one of them. Is it typically one per missile, or do you fire multiple per missile to ensure?
I'll explain. Just to give you the broader picture of this dual attacks by Iran. It was comprised of also cruise missiles, drones, and UAVs. Okay? With respect to the cruise missiles, drones, and UAVs, we had great support from our US allies. Okay? And most on the drones, cruise missiles, and UAVs were intercepted before reaching the borders of Israel by the coalition, which was led by the US and Israel. Okay? The ballistic missiles were intercepted only by the Israeli air defense system.
Wow.
Okay? Because they went out of space. Okay? And no aircraft can intercept ballistic missiles from outer space. and penetrated to our borders in the hypersonic mode, so very fast mode, very fast speed, and they were intercepted by our air defense system. So it was Arrow 3, David Sling, and the Iron Dome. 3 layers of air defense system.
Wow.
Okay. So now would you like to just review how it works?
Yeah.
Okay.
Yes.
So every defense operation, every defense system, and including air defense, starts with information, data. So you need to sense that an attack is looming. Okay? The earlier you sense it, the better the outcome, the higher the chances for you to intercept and to become safe. Okay? So the first layers are of detection and sensing are offline of sight layers, which are in space. Okay? So satellite monitor the Earth continuously, and if there's a potential attack looming, there is a focus of the satellite intelligence of the suspicious area. Okay, and the satellite can detect suspicious movement. Okay, and there's also a possibility to detect launches already from the satellite. If a detection is, if a launch, if an attack is somehow even partially detected by a satellite, it makes the task easier because you can apply multiple layered solution. Okay, so the second layer of detection, and this is the key and the core layer of the detection, is the radar. Okay, radar stands for radio detection and ranging. So radar transmits radiation, especially modulated radiation. It is the radiation, the waves are modulated, waveform is modulated in order to achieve a given set of performance: detection, classification, ambiguity, resolution, reduction of the false alarms, reliability of the tracking and of the detection, right? So you aggregate all of these factors, and then you create a scheme of how to modulate the energy that is being transmitted. Okay, so the radar, and this is a huge radar. I will soon share a slide if you want to see how it looks like. Transmits huge amount of energy, okay, to the air, and the radar processes the reflection. So the energy is transmitted, it intersects with targets, and a portion of the radiation, portion of the energy is being reflected back to the radar. Okay, based on the reflected energy, the radar applies signal processing algorithms. So it's like actual analytical mathematics, okay, to classify the target, and also artificial intelligence algorithms to classify the target. So the received energy in the radar undergoes both analytic signal processing and AI. And it has two major targets. One is to detect, so know something that is there, okay? To classify, to say whether it is a friend of a foe or a foe, a missile or an airplane or a helicopter, right? And also track. Track by mean we need to know the precise location of the threat in each frame, each millisecond, okay? And this is what the radar does. The radar scans the entire environment all the time, okay? There's no blanks, no blanks. The entire threat domain or potential threat domain of threat is being scanned by the radar all the time.
Wow.
Okay? So we have consistent eyes that works to hundreds and thousands of kilometers. The Israeli radars today can also detect and track satellites deep in the space, our space. Okay, so not just aerial target, but also space
Wow.
target.
That's
Yeah.
crazy. I
And
did
this
not know
is
that.
yeah. So this is the first layer. Okay, make sense?
Mm-hmm.
Okay. The second layer is the perception layer. Okay, the mission perception layer. It means now we are in the brain segment. We sensed, we know roughly what it is. Now we start the perception and planning. Okay,
Mm-hmm.
what's exactly the perception and planning? This is nearly hyperscale calculation that says how many targets there are, what are their routes, what is the optimal trajectory per interceptor that needs to be made in order to intercept all the targets. How many interceptor should be fired per target, right?
Right.
This includes the many parameters. It's performed by optimization of multi-domains in terms of security, probability of success, and also cost. You want to cost optimize throughout the mission, and
Mm-hmm.
AI do that in the perception there. So the outcome is the outcome of the perception layer is a full mission planning. Okay, and then after this is ready, there's a launch. Okay, so the interceptors are launched. Okay, and after the launch, there is, the missile updates the system, the AI system, the ground AI system, each frame on its location, performance. Maybe there's a problem with the missile, so you need to launch another missile. Maybe there are other, unseen or surprise in the scenario that needs specific reply in real time, right? So there's a direct communication between the missile and the computational station that does the perception and the planning in real time. And then the missile is autonomous. So the missile has eyes itself and brain of itself. Because as you know, like human beings, the closer you get to the target, the better you see it, the more information you have, and you can make better decisions.
Mm-hmm.
So at some point, the load of the mission load goes fully to the missile themselves, and they chase the targets. The target maneuver, they respond. If they see that this is a friend, they avoid the targets and explode or fall to the sea, right? All of that, and everything is in the missile of that space. And then there's the end game stage. So the end game kill chain. What does it mean? So what's the target? How am I going to intercept the target? Whether it is a hit to kill, or I should activate a warhead. Is this target is nuclear? Because if it's nuclear, I want to intercept it in a specific way that will not activate a nuclear reaction.
Right.
Did that. Or if it's a conventional threat, I can use a warhead and improve the chances of interception. So these operations are made in the missile's eyes and brains. Okay,
Mm.
it's called seekers, radar seekers. And they control also the controllers and the body and the engines of the missile to deliver the interception mission.
Wow. That's crazy. And that's how you can take down 200 missiles coming at you all at once,
Yeah,
you know.
actually 300 missiles, ballistic missiles.
Three, yeah, but who's
200
counting?
is the upcoming. The October attack is 200. The April one is at 300. And this is again the largest ballistic missile attack in the history.
That's crazy. I mean, that's just wild. And
Yeah.
all these parts, of course, have to come together, as you suggest, in real time. I
In
mean,
real time.
one of the
In
tricks
real time.
that the bad guys will use is to send a whole bunch of drones and try to chew up the awareness of the system and then send in the
Yes.
real missiles after
Yes.
that, right?
Yes. Yes. This is this is a very good comment.
Mm-hmm.
Yeah, I thank you for this comment. I appreciate it.
Yeah.
Um, the reason is the reason that this comment is so important is that the air defense systems of today were designed for missiles threats. They're designed for airplane threats, helicopter threats. They were not designed for the current and future threats, which are drones,
Mm-hmm.
vertically launched hypersonics, cruise missile hypersonics, extremely maneuvering hypersonics, drones and swarms of drones,
Mm-hmm.
right? The, the, the air defense system can very well cope with fast targets and high flying targets. They cannot well cope with slow targets and
Hmm.
low altitude targets.
Interesting.
Amazing. So these are new type of emerging threats that makes it very difficult for today's system to intercept, take care of. And we see
Mm-hmm.
that in Israel and Ukraine.
Mm-hmm.
Okay. And dwelling for a minute on the drones and the swarms, China manufactures 7 million military drones a year.
Oh my Lord.
You know how many the US manufactures? 200,000.
Wow.
Okay. So the next attack would be an orchestrated attack of drone swarms that currently can barely get detected, okay? Can barely get classified. No radar in the world today can differentiate between a bird and a drone. So currently there are air defense missiles that fire missiles on birds because they are confused between the birds and the drones,
Mm-hmm.
right? This is the situation. These threats are also cost effective. So they cost, let's say, $5,000 a threat. And you cannot intercept 5K threat with a $2 million interceptor.
Right.
This doesn't scale. This
Right.
creates an economic warfare
Right.
also,
Right.
right? And they can, so intelligent adversaries can exhaust us economically.
Mm-hmm.
We need to take this into attention. We need to be aware of that while building the Golden Dome, the future air defense systems. We need to be aware of that.
Yeah.
And the threats are software defined. So not more a missile with a predicted route. There's a drone that can create any route in the world. And by releasing a new software version, you can completely change the behavior of the threats and actually the threat itself.
Mm.
So the new threats are cost effective, autonomous, swarm, and software defined.
Wow. Well,
Okay.
and I wanted to ask you too. I'm just guessing here because you've got a an AI system. You're of course focused on algorithms of physics and how things
Mhm.
fly and move, but also you have pattern detection and classification. And I'm guessing that the
Yeah.
system is designed to recognize new patterns of behavior and then identify those and classify those. So you get a new missile
So,
that's
mhm.
acting in a way you haven't seen before. Now, I'm guessing there's a way to identify that as a new pattern, as an emergent behavior, and classify that. Now I know what that is. So maybe can you talk about how the system learns from new experiences and how that is persisted and
So
leveraged in the future?
good, good point. So in order enable the next generation Golden Dome, you cannot count on existing sensor stack.
Mm-hmm.
Why? Because existing sensor stack are optimized for missiles and airplanes, not for drones and UAVs. They're not general.
Right.
They're designed based on assumptions. Okay? And the main problem with that is the resolution. Okay? The resolution of the radar is the biggest sensing problem of air defense systems today. And I give you an example to quantify, right? Some numbers. So the pixel size of an average air defense radar is roughly 100 meters.
Wow.
So imagine a picture with a pixel size of 100 meters. Okay, so every target that has altitude of below 100 meters is considered today as a ground target.
Wow.
Yes. So this is why, in order to intercept cruise missile, you need either ships or airplanes, because the air defense radars have very low pixel size. But this pixel size is not only on the space, it's also in the velocity. Okay? And in the velocity is like 300 kph, 100 miles per hour. So every target that flies below 100 miles per hour is considered as static target.
Wow.
Non-moving target.
Right. Even though
Okay?
it's moving 80 miles an hour.
Yes. So today's threats, and this is a huge problem. One of the problems that we solved in Apex is that the resolution of today's air defense sensors does not get even close to what's needed in coping with new threats. Okay? So just to give you an example, at Apex, we developed a 4-dimensional imaging radar with resolution of 3 centimeters. So what is like 100 meters in today's solution is 3 centimeters in our solution. This is what makes us not predict, directly sense the trajectory. We're not guessing. We sense the trajectory in real time.
Wow.
Understand? And this makes what makes the interception much more solid, okay, and trustworthy, also for the new threats, not just the old threats, but also for the drone swarms, and UAVs. And now, do you have more question on the sensing and trajectory part?
I mean, I do, but keep going. You'll probably answer it as you talk.
And now there is the AI. And not a lot of people talk about that because of the lack of experience, of technology and operational experience in that domain. But we need that the system needs to classify the targets. You need to know whether it is a drone or a bird, whether it is a UAV or a vehicle. You need to know that. It's not just something and know that something is there. The system needs to know that this is a threat and the class of the threat to launch an interceptor. Okay? How do they know that? This is not GPT. There's no textual information that tells you about the physical signature of a drone, right?
Right.
You cannot label the data. You know that if you look at today's AI, it is either like ChatGPT, GPT-like, which works on self-supervised learning, and then human feedback, like a reinforcement learning with human feedback to create the guardrails and optimize the models, etc. There is no way that such information exists on the internet, and you cannot create guardrail by human, because human cannot see a radar signature and know what it is. No one else. So this is a new class of AI, right? So on top of the high resolution sensing, extremely high resolution, there's a breakthrough in resolution. It's a foundational breakthrough that overcomes theoretical bounds. Been working for that for more than 15 years to reach that.
Wow.
You need a breakthrough in AI. How do you know that this is a drone from 15 kilometers? You cannot label it. No human can label it. So how do you do that? So we developed a new multi-physics and AI that knows that automatically without human labelers. Okay? In the classical computer vision and AI, you know, like companies like Scale AI, which is a famous company, they employ 250,000 manual labelers and data workers. This can never scale, right? Can never scale. So you need to do it in much higher level of data complexity, and you need to do it fully automated in order to get the strategic advantage. And this is exactly what we do. This is like the under the hood of what enabled us to get the result that we are now getting.
Right. Well, you're using deterministic algorithms as opposed to stochastic or probabilistic, right? I mean, that's, if I understand it correctly.
So first and foremost, all of our pipelines, AI pipelines, is automatic. No human in the loop. No data labelers, no manual backend of AI. You know, the backend of AI is like, you know, there's an image from the Industrial Revolution, right? The AI is very nice and glamorous from the outside, but the backend is like thousands of people labeling data, guardrailing the GPT. So the huge backend paradox in AI. We don't have this paradox. We do everything fast and automated versus the slow, non-scalable, and manual of today's AI backends. Okay.
And so how did you train this model is I guess my big question, right? Like what's the input that you would use, because you're taking data from radar, you're taking telemetry data basically, right, from radar, and you're taking visual data and other forms. So these are, these are unwieldy sources. They don't really fit into a table in a data
They
warehouse,
don't. They
right?
don't.
So how did you train that?
So I think that you touched you asked the most critical and most confidential, of course, question on
Right.
how it's being done. So you cannot do it the way it is being done today.
Right.
You cannot do it.
Right.
No, no taking missing piece of the puzzle and completed by sentence. No, then estimation, sample generation. You need to do it completely different. So what we do is start from the basic mathematics. Okay, we build analytical signal processing pipelines for each of the sensor modalities we address. So it is radar, LiDAR, GPS, IMU, camera, and acoustical sensors.
I see.
So by analytical pipelines, I mean how the signal is being processed from the moment it is converted from analog to digital until the output is created. So we have specialized pipelines for each sensor modality.
Interesting.
And then we fuse them. And then we have multi-frame processing on all of them. And then also we have the AI on each of the sensor modalities and also the fused information. Okay? A bit of how we train it self-supervised and weakly supervised. And we use a lot of physics constraints and physics equations like continuity, causality, momentum conservation, and memory to improve and strengthen the model, and gives also some physical implication. Okay? And the outcome of that is multi-physics foundational AI models that are trained on all of these modalities, and they can predict and generate sensor data very high fidelity. Okay, based on these models, we build expert agents, expert interception agents that are expert, in autonomous interceptions. So to this huge multi-physics AI model, distill it, build expert interception agents on top of it, and this is the final software that is deployed.
Wow. That is so incredibly cool. I like the
Right.
way you, because what you instrumented the environment, right? I mean, that's what the sensors are. You've instrumented the environment, and as you suggest, you're catching radar, lidar, visual optics, and also sound,
Yeah.
and then you're leveraging a baseline of understanding of material science, of the physical properties of these objects, how they move, how the weather conditions might affect that, for
Exactly.
example,
Exactly.
right? You're scanning all these things. That's one hell of a processing engine. I mean, goodness gracious, is it?
Exactly.
I'm just curious, and feel free to not answer questions because there is proprietary stuff involved here. But I'm guessing that you have clusters, and do they spin up new clusters like when there's an attack? Is there does it spin up additional clusters to be able to handle the additional input, or how does that work?
It's quite sensitive, but I'll try to answer. I'll try to
Okay.
answer.
Thank you.
First and foremost, you will be surprised to hear and to learn that our models is much smaller than today foundational model.
Hmm.
And the reason is, and it's again, it's quite sensitive, that the mechanisms that we use in the training process
Mm-hmm.
improve the precision of the model without any human in the loop.
Hmm.
So there are barely no neurons that are wasted on AI shit, AI crap, like the spontaneous stuff, the
Interesting.
non-control stuff. So we give the data guidance. I try to select my word, right? In the training process. So we get much more accurate models, but smaller.
Hmm.
Okay. So first and foremost, we build the AI model in such a way that they will be compact and precise and
Mm-hmm.
robust multiphysics, right?
Mm-hmm.
And this is a very sophisticated uh, like an investor that looked at us recently said that this is like 2 decades ahead of DeepMind from Google.
Wow.
Uh, and for me, it's like to say the least, right? Because this is like a new dimension of AI. But this is
Right.
what we need to do in order to face hypersonics and swarm.
Right.
You cannot do it
Right.
differently,
Right.
right? So this is one. The the other stuff is that the other parameter is that we build specific software kernels for everything. So we're not just guesstimating and throw it on we design the software in such a way that it is optimized to our compute resources.
Mm-hmm.
Okay. And by that, it also reduces the computational load. It's still a huge computational load, but it is much more manageable in that way. And then yeah, clusters and everything that you said.
Well, and I think it's important to focus on signal processing. And you've got these multiple streams coming in
Mhm.
simultaneously. So
Yeah.
that's how you're able to see the big picture and understand. And I'm guessing that each one of these little engines has its own intelligence baked into it. So it's sensing what's happening. Going, uh-huh, okay, this looks like X. This guy goes, hmm. And there's a sort of an overlay that's pulling this information together. You look at there's some interesting companies doing what they call causal models these days, where instead of the old-fashioned way of looking for of trying to map a schema to a set of activity,
Mhm.
instead they're getting more clever about the how can I describe this? About the model that they apply to the world, and does this match or doesn't it, basically. And so once you've found a model that does match, think of like, fraud detection and things of this nature that are much more commonly seen in the world. Once you detect a certain pattern of behavior, then you're just kind of watching for that all the time. And in the runtime, it's okay. Okay, is it this? Is that? Is it this? Okay, no. And then the runtime again. Okay, is it this? Is it that? Is it this? Okay, no. But what you're doing with having all these different signals is you're giving this real time view of the world, right? Where the intelligence underneath is trying to constantly map what's
Yeah.
happening, right? So you have these layers that are they're in the runtime and they're constantly updating, right? To be able to address changes in this environment. And then you have to fire up how many ever missiles to solve these guys, and is there another one coming? I mean, it's
Yeah.
just I'm fascinated thinking of the runtime itself. Like, what is it processing? And I'm guessing it is a very, very tight, succinct runtime that goes on and on and on. And again, you could spin up other clusters to not compete for resources on this one. Like, I'm focused on that missile, he's focused on that missile, and you want those to be independent of each other, but still fed by the main system. Is that right?
Yeah, it's quite right. Let me first and foremost explain a bit deeper,
Okay.
okay, about how it works. So the the environment is of 4 dimensions, okay, not 2 dimensions like a
Right.
camera. Camera is 2 dimensions.
Right.
So everybody say, okay, we are going to do like military grade air defense with cameras. Not going to happen. There are the third dimension, so there's the 2 dimension, like the height and the width.
Mm-hmm.
Third dimension is the depth,
Mm-hmm.
how far you are from me, or
Mm-hmm.
how far is the target from the system. And the fourth dimension is velocity.
Mm.
Okay.
Oh,
So
interesting.
zero velocity is static object, but each object has velocity. So our technology measure directly all 3 spatial dimensions. So X, Y, Z, and velocity at 3 centimeter resolution.
Wow.
Okay, so you don't guesstimate. By the way, most are guesstimating because the pixel size is so huge, you must guess. When you
Right.
don't know, you guess. We know, right? You don't guess. And this I think can solve the paradox. So we transmit, we cover the entire space with electromagnetic radiation, the modulated radiation, what I told you. We received raw energy into the sensor aperture, and then we create the 4 dimensional processing first and foremost. First of all, we extract the range information. Afterwards, we extract the velocity information of everything in the environment. We don't filter in that point.
Hmm.
Then we extract the spatial information, so the azimuth, the horizontal, and the elevation, the vertical information. So then we have a cube, okay? And within that cube, we perform more complex algorithm like super resolution, physical super resolution, how you improve the resolution beyond the theoretical bounds to get to the 3 centimeters. You cannot do it with conventional systems, okay? If you want a 3 centimeter resolution air defense radar, it will need to be in the size of Manhattan. Cannot do
Wow.
that, right? So you need to have sophisticated algorithm to improve the resolution of the sensing. So we improve the resolution, and afterwards we perform detection. There's a lot of noise. We need to filter false alarm. We need to filter all the artifacts of the hardware itself. So we filter,
Right.
and then we create, and then we get 4 dimensional representation of the environment itself at high resolution. Okay, this is the basic. This guy is inputted to a tracking. So in order to know everything in each step of the time, okay,
Mm-hmm.
and to the semantics model
Mm-hmm.
that gets the shapes, the reflectivity, the spectral signature, the velocity vector, all of that, and then it can create the semantics. Okay, and now we have semantics map. Okay, once you have the semantic maps, you know the target types per location, and then this is an input to the planning and mission execution state.
Mm-hmm. Mm-hmm. That's
So,
fascinating.
so yeah, so the once you have the environment segmented semantically and also measured, it's not enough to get the semantics, because everything changes. So you need
Right.
to measure everything in real time. It's
Right.
not like one time. right? Because missiles are maneuvering. You can have occlusions, you can have swarms, you can have suddenly an airplane getting it. You need to know everything in real time, including the 4D processing and the semantics.
That's crazy.
Input that to an intelligent mission planning and execution layer, and it will decide what type of interceptor to use,
That's crazy.
how many, and yeah.
That's amazing. I mean, it really is. It's what a phenomenal system. And to your point, it's automated. I mean, you developed the algorithms for all the signals that you're pulling in, and then the brain underneath is the planning and execution based upon all that input and the tracking, right? Because you're tracking, and I'm guessing you're also tracking like when it hits, how it hits, like all that data gets fed back into the model at some point. Is that right?
Yeah, exactly. And what's nice is that since everything is automated, it's getting upgraded all the time.
Wow.
It's self-learning.
Right.
Today's systems, you need like the threats research division that we look for threats and classify them as new threats, and then a huge process in terms of timing, planning, developing, execution, deployment, release per threat. Here, everything is automated
Right.
because of the resolution and the AI.
Mm.
Okay, both of them. And another data point is that we developed the hardware and the software.
Oh,
Hardware and software. You cannot improve the resolution of existing hardware by orders of magnitude just by software,
right.
especially with four-dimensional information processing, etc. And so if this would have been possible, everyone would have done that, right?
Mm-hmm.
So there is a tight hardware-software coupling. So the first step, we thought, okay, let's be a software company, software-only company. This is the easiest stuff, right? You can just SaaS B2B everything, right? Because
That's pretty funny.
yeah, this is the easiest, right? But and we have like the hardcore of stuff is how we improve the resolution. This is without resolution, you don't have anything. A bird equals a missile equals that. Without a very small pixel size in all 4 dimension, nothing is possible, right?
Right.
We will go. So now in my PhD, one of the breakthrough that we had is inventing a new class of algorithms that improve the resolution below the physical bound. So it's like a theoretical limitation in the literature for resolution.
Mm-hmm.
And we did 10 times better.
Wow.
Okay. And now we try to test it on existing hardware and nothing worked. It's broken. It maybe gave, instead of 10 times of improvement, it gave 10% of improvement.
Wow.
And then we researched and understood that hardware limits the algorithm performance. So we had to iterate hardware, software for 4 times until we got to balance the system and get an operational grade super resolved for the system.
Wow. So, I mean, that makes a lot
Very
of
deep, right?
sense. That makes a lot of sense because, so I've tracked this industry for a long time, and we had a guest on the show years ago who made this really interesting point. He said, well, first of all, innovation always starts at the hardware level, right? And then it sort of builds up the stack theoretically. And he said, you'll see appliances come along when the traditional software environment won't get you what you want. So that's when you have to start going back to the hardware itself, to the physical, the chips, the boards, the inputs, everything that goes into this. And what's interesting is because it's bespoke, it is that much safer, right? Because you've
Exactly.
designed your own hardware and your own
Right.
system. It's harder to hack because the systems used to hack are predicated on the uniformly available or regularly available hardware, which you don't have, right?
And bear in mind that this is not a camera or a text, right? This is 4 dimensional.
Right.
Okay? And the system transmits wave. We have waveguides and antennas and interposers and transitions So this is much more complex than just a camera, for example.
Wow.
Okay, so we tried, and to be honest, my first idea was to do it as software only. We prayed this would happen, and once it was broken, it made us go back to the physics, to the foundations of systems design, physics, radio frequency, millimeter wave radomes, antennas, arrays, spatial sampling, MIMO, code space and time coding, all of that in order to co-optimize physics, hardware, and software. And then it happened, right?
Wow. That's wild. I mean, so I'm wrapping my head around how long it took you to get here and how much trial and error was required to do all that. And you think about there are so many constraints to traditional ways of doing things. Like, for example, stream processing in of itself is a bit of a science. Time series databases are designed to be able to optimize the leveraging of time signatures, right? But that's a very specific architecture compared to a relational database or a vector database, for example, which is very different in terms of how it persists information and then how you then pull it back. And you guys had to roll your own across the board, right? I mean,
I think that, look, I think first and foremost, it's about the people.
hmm
It's about the people. And, they say that culture eats strategy for breakfast, right? So we are always shooting very, very high. Shoot for the moon.
yeah,
And we nurture a culture of excellence, of literally survival mentality, like
yeah,
like in Israel,
sure.
and never say stop, never say this is enough, and never say that this is impossible. Everything is possible.
Wow.
And now you combined it with social values, okay? Social values, because our team is like a team of geniuses. Genius. I'm the luckiest person in the world to lead such a team, right?
Wow.
But and I'm, each day I wake up, I'm just grateful.
That's
And
outstanding.
yeah, we have one of the guys one of the most senior guys that works for Apex is Major General Dr. Yaakov Benjo. He's a equivalent to a 5-star general, and he was the J8 of the entire IDF.
Wow.
And this is in contrast to the US, when you have the Army, the Air Force, the Navy, the Israeli Army is a one system.
Hmm.
So Major General Dr. Banjo orchestrated and architected the full military system: space, air, sea, ground, underground, cyber, and digital. So he was planning and executing everything from quantum computing to F-35 and cucumbers.
Wow.
And this guy works for us as a chief strategy officer. And going back to the people, it's not enough to hire the best people and set high goals. You need to install values, human values. And I think my favorite example is customer obsession, right? And I took and I learned a lot of Jeff Bezos. I
Hmm.
like Jeff Bezos as an entrepreneur. I think is phenomenal.
Mm-hmm.
But what I did what I did with when building the core values of the company is going deep, okay, and trying to future proof, trying to look for the problems in 5 years, 10 years from now, and build a scalable set of values.
Hmm.
So what I did with the customer obsession values, which I love, is take it not is expanding it, not just for internal customers, but also for external customers. For example, if one group inside a company to deliver content to another group, so this internal group is the customer.
Mm-hmm.
So you need a customer obsession to be also internally,
Mm-hmm.
people to be responsible for the success of the other team,
Right.
right? And you measure your team by also by these values. And now you get a winning machine. Best people, high standards, strong core cultural values, and this is how we do that.
Well, and you've imbued that into your team, so I bet you're gonna like this concept that I've thought about for many, many years now. In many organizations, and even between organizations, like between governments and the people, for
Mhm.
example, you will get this dynamic of us versus them. And it happens
Yes,
all the time. It's like
yeah,
country to country, it's us versus them, but departments, marketing versus sales, us versus them. And that's what you need to watch out for. Because as I say, there's no them, there's
yeah,
only us.
exactly.
And we must
One
work
team.
together to solve
Exactly.
these things, right? And so, what's really interesting too is like the power of AI and Gen AI and GPT, for its shortcomings, it is allowing a real leveling of the playing field. And I think that a lot of the troubles that have plagued organizations and even countries and governments over the years stems from these sort of almost Byzantine hierarchical structures where you have, the boss is up here and that all these people report to him. It's this very up and down sort of stovepipe architecture that is extremely inefficient. It's not efficient at all. And, for example, I won't name the company name, but it's a very, very big software company, and I did a lot of work with them. And I would notice when we would have calls, if there were more than four people on the call, especially five or six, no one wanted to say a word because they're all afraid. They didn't want to either upset someone or reveal that they didn't know something. But my point is, all of that is fear based. Whereas if you have a culture of openness where people are encouraged to speak their mind and to challenge things and to wonder about things, that's when you get cooperation because people don't take it personally. You have to realize we're just learning, and I want to learn from you and all these team members. And when you have that idea in your head, you need to speak up and tell people something, right?
And yeah, and you reached the second value. The second cultural value is transparent feedback
Mm-hmm.
and constructive confrontation.
Mm-hmm.
Okay, so we strive for that. So it creates transparency. It creates teamwork. You are expected to say what you need to say. You should be polite, should be professional, but you're expected to provide this value to the team.
Right.
You're measured by that.
Right.
Okay, and suddenly there's no like bubbles. There's no transparency issue. Everybody is aligned with the target, what needs to be done, and with the problems. Because
Mm-hmm.
there are problems in any organization. Every organization has its problem, right? So such value sets helps you solve the problem.
Mm-hmm. Yeah, that makes a lot of sense.